Okay, we're going back a little bit just to get you guys squared away. So we talked a little bit about sample size. Is it better to have a big sample or a small sample? Big. Okay. What happens is the bigger the sample, the stronger the power to actually detect a difference, let's say. So when we actually run an experiment, remember with the ants, all they showed was individual ants. Here we go. Okay. Okay, so right here was a regular ant, here was a long-legged ant, and here's the one that got chopped off, right? If you remember that. It just showed one of each, right? Now, is this a big sample or a small sample? Okay. In fact, it's so small, it's not even a sample. It's one individual of each. And when we take a sample of a population, unlike, let's say, counting the whole population during a census, you can get a sample and it gives you an estimate of what that characteristic is for the population. Okay? The thing is, if you only have one, what's to say that one of those ants is not faulty in being able to count? Right? Some people are better at math than others. Some of these ants might be able to count better than others, right? And so you might end up with an ant that it looks normal, but it's not because it really can't count. So that's why you want lots and lots and lots of replicates is what they're called. Okay? So in other words, you take all these ants and you apply the treatment to, let's say, 100 ants of each, right? 100 ants of regular size, 100 ants of stilts, and 100 ants of small. Okay? And then you run the experiment. That way you're probably going to have a representative sample. If you have some faulty ants, it's no big deal. For the most part, you're going to get results that actually show that the ants can perhaps count. Okay? Now, so you have to make sure in terms of sample size to always have as large a sample as possible. But it's not always possible. Okay. Now, let's see, what was it? Oh, one more. Okay. If you remember, the German scientists who did this, and this Swiss guy, they were all guys, right? For too long it was thought, women can't do science, women can't do math, well, BS. I know women mathematicians who, well, leave me in the dust. I know great women scientists, so I just want you to be aware that there are lots of women scientists now. There's more and more and more, especially in biology. And in applied biology as well, such as becoming a doctor of medicine, right? Or a dentist or something like that. In fact, I think our med schools are graduating more women doctors now than there are actually men doctors being graduated. Okay? So, I just want to kind of clear that up. Okay, just to go over a few things. Um, in terms of subject bias, so with those ants, did they know which treatment group they were in? Huh? No, yes? No? Why no? That's okay, just, I don't care. I don't care about the answer. Yes or no, and why?
To not have any bias in the experiment.
Yeah, I know that, but did these ants in that experiment actually know which treatment group they were in? Well, they've got a small brain, but do you think, let's say someone lopped your legs off, would you know what treatment group you were in? You would. Okay, so now we don't know that ants actually, they kept walking, even though we lopped their legs off or on the stilts or whatever, but that's one of those experiments where you can't control subject bias. In the perfect of all in the best of all possible worlds, you would have a situation where individuals who got a specific treatment, let's say vitamin C, they didn't know which group they're in, right? It's called a blind experiment. In terms of the treatment group, the ones, in this case the ants, who were not, their legs were not modified, they were the control group. Were they treated the same way as the other ants? In the different groups? What do you think? No, exactly. So in this case, there's subject bias. Now, if this was a vitamin C experiment where individuals were given vitamin C, a tablet, let's say a yellow tablet, and then the other group was given a placebo, looked like the same tablet, would that be a blind experiment? Right. Okay? So those individuals wouldn't know which group they're in. And that's controlling for the placebo effect, which is a real effect measured. So you're more interested really in terms of vitamin C. If you didn't control for that, you wouldn't know, was it the placebo effect that some people didn't get as many colds as others, or was it the treatment actually doing it? And so having a blind experiment in terms of subject actually lets you measure that and not have a confound. The confound in this case would be knowing which group you're in. Okay. This is kind of going over stuff we already did. I just want to make sure you understand. In terms of the experimenter, you want those individuals to be blind too. If the experimenter actually knows which individual is in which group, there's a problem of even unconsciously measuring something that's not there. Because you think, oh, this person, I know this person is getting the drug, this person isn't. Okay? Now, like with the cold business, you might actually measure the cold just by looking at the individual, seeing if they have a runny nose and all that kind of stuff. Or you actually might go and measure, take a swab and look at viral particles from the nose swab, right? But the main thing is, with the technician or the experiment, you want that to be blind as well. In other words, now I know they're designing the experiment, but there's a way to make it so that they don't know which individual actually received the, let's say, the pill with vitamin C and which one didn't. Okay. And I mentioned a little bit about confirmation bias. Everybody, well, I won't say everybody. Many people think their ideas are great. that, oh, I can't be wrong or whatever. It's a natural sort of thing. I came up with a great idea, it's a beautiful idea, and yet it's actually not a representation of reality. Well, that's one thing in terms of, we know how people are. Obviously, they don't want to look for evidence that kind of confirms what they believe their hypothesis states, right? And so you have to be very careful, and in science, about confirmation bias, actually finding out what you expect to find versus finding out just what the experiment shows. Okay. This is something I kind of added. Statistics, population. Now, population census is different than a population sample. A census, you go, now, in statistics, the operative word here is population. Doesn't matter if it's a population of people, of animals, of plants, of widgets. Let's say you've got a manufacturing plant, and they're producing these gadgets, right? And they want to make sure, in fact, that the gadgets are working. You're not going to check every single gadget to make sure it works. You're going to take a sample of it. And you can get a pretty good estimate, especially in terms of sample size, of whether you're gonna, if there's a difference, let's say, oh, we think there's a 1 in 1,000 chance of getting a bad widget. And when in fact you actually run it, and it turns out it's 1 in 100. Okay? Now, we have kind of different kinds of statistics. Anybody know what an average is? Anybody know not what an average isn't? Who doesn't know what an average is? Okay. It's actually called a mean. That means it's a mean is an average. So let's say I took everybody in here and we measured your height in inches. And then divided by the number of people that we had, we'd get an average height. That's the mean. Now, sometimes we actually go instead for what's called a median. And the median is the individual right in the middle of the group. Okay? Now, the difference between the mean and the median is that the mean can be influenced by, let's say, an outlier. Let's say one of the individuals I put into the database, I accidentally showed that they were 1,000 inches high. Okay? That would be like an outlier, and it would actually influence what that number said. A median can never be influenced because you're actually taking exactly the individual of a certain height who's right in the middle of the distribution of heights. Okay. Now, there's also there's also something called inferential statistics, and we did a little bit of that, and we'll do it kind of again. About, is this group sample from this group different from this group, or this population from this population? That's called inferential statistics. It's all based on what's called probability theory. In other words, the likelihood that something is true, it appears the data shows that it's something that's true, versus something that actually isn't. Okay? Now, there's this famous line. It was attributed, I think, at one point to Mark Twain, but it's actually Benjamin Disraeli, I think, who was the Prime Minister of Great Britain. There are 3 kinds of lies: damn lies, and statistics. And this is part of your education in science in terms of when you're going to read something in the future, let's say an article about science, or whether it's, let's say, a population, you want to right now they're doing polling. They're taking samples to find out who's ahead in the election, right? And they usually give you a margin of error, plus or minus 3%, plus or minus 5%, whatever. Well, people use numbers. For some reason, our heads think, oh, we see a number, it's got to be true. If you see a number without any sort of plus or minus error around the sample, because the sample is, remember, it's a sample. It's going to be, hopefully, it's somewhere close to what the actual population shows, but you can't always measure the whole population, right? Like in a census. So people use statistics or numbers to lie to you all the time. You say, it turns out that 90% of people believe in UFOs. You could do a survey and ask people, do they believe in a UFO? And depending on how many, you would actually end up with 90, let's say it was 80% plus or minus 5%. So if you see a number without plus or minus around it, it's meaningless. Okay. Now there's, so I wanted to bring up the mean, right, the average in the sample, the standard deviation. You want to know around the mean for a population, let's say height, you want to know how much variation there is around the mean. Not everybody is 6 foot tall. There's probably going to be a wide variation. I'm not 6 foot tall, right? So I'd like to be 6 foot tall. I think I should go into talk to those individuals about the ant experiment, and maybe I could get my legs lengthened or something like that. So the main things in statistics that we're really concerned about is the mean different in two populations, and the only way you can do that, to determine that, is if you actually have a measure of variation in terms of your sample. And then the probability that two samples are different in terms of the population. That's where you use inferential statistics, and you need that standard deviation. Now remember, there's not only the sample size, but there's an effect size. How big of an effect is there? And then finally, the variation between samples. Okay, so I think the top hat gets a little bit into that. There's gonna be test questions on that as well. So if you don't understand, I'm not gonna go through a whole statistical, we're not gonna do that in this class, but I want you to know how statistics are used and how they should be used. Okay, and then remember, this is, we went over this, someone flipping a coin, there's a 50% probability that it's going to come up heads. If you flip the coin, each individual flipped the coin 10 times. It turns out the first individual came up with 6 heads and 4 tails. Another individual, 5, 5, 5. Another, in the other group, some individual flipped a coin, was only 2. You could actually get, just by chance alone, small chance, you could end up flipping a coin 10 times and get 0 heads, for that matter. Okay? So we can actually find out whether there's actually a difference in this group. If you actually added up the scores for each of the 4 individuals in each group, one would be 21 and the other would be 19. Would you know, was that significant? Well, I'll tell you right now, no. Even though it seems like it's different, the significance level, we usually say 5 out of 100, is the probability is much higher than that it's actually the same same coin, right? You should get 5 and 5. Now, as you know, since you're only flipping it 10 times, that means for each individual, you have a sample, one sample. Between flipping a coin 10 times, each difference that you have, whether it's 5 or 6 or 7, it's 10% out of 1 out of 10, right? So you can be off by 1 out of 10. You'd expect 5 and 5, but it should, sometimes it's not that way. And then when you get something like 2, that's pretty different than what you would expect. Doesn't matter, it's actually what came up. But that would be way off from what you would expect. So this, in this case, if we actually did this flipping the coin thing, we probably want to do each individual flips the coin at least 100 times. Then it would only be, instead of 10%, it would be 1%, or 1,000 times. Take longer, of course, but that's 1 out of 1,000. So let's say you flipped 1,000 times. Some individual might end up with, 551. Another individual might flip the coin and end up with 499. The chance of ending up with an individual who flips the coin and with 200, or let's say 220 out of 1,000, it's going to be very, very low. Because of 1 out of 1,000, so you end up with a coin flip. You're going to be much closer to the true mean, which is, in this case, is 50%. So this is an example of why you want a large sample. Okay. And I went over this a little bit earlier, but let's do it again. Okay. So here's our vitamin C consumption. You had individuals who ended up with, let's say, almost 90% colds. They didn't get the vitamin C. And you ended up with 1,000 milligrams. Now, if there were only 10 people in each group, now it seems like this is a big difference, right? But if there's only 10 individuals, it might not be significant. There might not be enough power. So let's say this is a small sample. Come on. And the error bars, just the variation, would be very high. And they would overlap if this was a very small sample. In this case, you wouldn't, even though it seems like there's a big effect size, there actually isn't, because there's such a small sample that you're actually dealing with. On the other hand, we had this. Now this looks like there's no difference. But if each sample was 1,000 individuals, your your variation around that, because you have such a good estimate with so many individuals, you might find that and these are the means, and then the standard deviation around that mean. Do they overlap? No. This actually might be a statistically significant difference in terms of who gets a cold and who doesn't. So in this case, people who didn't get vitamin C, they got 60% colds. Those individuals who got 1,000 milligrams, only 50% of those got colds. There was a 10% difference. That could actually be meaningful, okay, a real significant difference. If you had a cancer drug that had that much variation between, let's say, one cancer drug and another, you'd say, oh, it's saving 10% more people than the other cancer drug. Okay? Okay, I talked about this already, about you can't always do perfectly controlled experiments. In other words, where you get rid of subject or experimenter bias. Sometimes you're just going out and using an observation. That's called an observational experiment. You can still make a hypothesis and make predictions, but you just have to go out and measure things how they are. You can't assign randomly individual subjects to a treatment group. This is especially true in, let's say, obesity. If you're just going out and measuring, okay, this person is this big, you're not applying or randomly assigning people to groups. They're already in groups. They already know that they're fat or thin, right? And so you can't make the kinds of inferences that you would like if you actually did an experiment. Now, if you did an experiment and you wanted to check different diets, you'd enroll a whole bunch of people, and some people would, let's say, eat a diet high in complex carbohydrates. They just, they eat cake all the time, versus someone who's on a low-carb, high-protein fat diet, right? You could do that, but a lot of times when they just give you a rate, they're just going out and asking, saying, oh, what do you eat, and how does that relate to the diet you're on? Okay. Okay. Talked about a theory. A theory is not what we talked about in terms of, oh, it's only a theory, like gravity is only a theory. When someone says that, that's an opinion. And I would always tell them, well, go up to the top floor of this building and see how gravity affects you by jumping off. Right? Okay, so when we actually have a scientific theory, it's a different animal, like the germ theory of disease. Before this, no one knew about microbes. God damn it, it should automatically do that. Okay, so model organisms. So you can do the things to model organisms that you can't do with humans. You also can find out, like we know the complete genome of each of these organisms up here. Okay? They have DNA, just like us. Some of the DNA that we share, we actually share more with, let's say, the mouse, because we're more related to the mouse. We had a most recent common ancestor with a mouse about, 60 million years ago. We probably shared a most recent common ancestor with the roundworm, probably, let's say 500 million years ago. The fly, a little more recent. E. coli, we probably had a most recent common ancestor with E. coli and humans, probably, maybe 2 billion years ago. Okay? So we've actually got the genomes for these, and we can see the number of differences. And we also know what a lot of the genes do, so we can actually experiment on them. A simpler organism, if you're, let's say, you might want to look at behavior. Well, if you want to look at behavior in terms of the nervous system, a mouse has a very complex nervous system, like we do, a vertebrate nervous system. A fly has fairly complex, but the best organism here would probably be the roundworm. It's got a very simple nervous system, but it's still, you can look at behavior. Like, do roundworms actually have memory? You can ask that question, you can answer it with a roundworm. It's sometimes easier to do things when it's simpler compared to more complex. Obviously, we have to learn about science or what some of the new findings are. We have to share it. And there's different kinds of method. There's primary source literature. So we have a professor here who does work on those roundworms I was telling you about, Cheryl Van Buskirk. And C. elegans is the roundworm. And she actually had this published in a scientific journal. This is called primary source literature. The kind of stuff that you probably would read about would be in secondary source. Magazines, radio stories, television, interviews. And the people who are doing those stories have actually read the primary source, and then they kind of summarize it for you. On the internet, you have to be careful about this because, well, people are reporting all sorts of things that are obviously untrue. Okay. And then, how does science change and progress? Well, do you think there's scientific progress? Anybody think there isn't scientific progress? No one. Okay. You guys aren't skeptical, are you? That's too bad. Okay, it's good to be skeptical. Because as we've learned, sometimes we think things are the way they are, and they turn out not to be that way, like the fact that bacteria actually causes a certain number of ulcers in people, and it's not just because of stress. Okay. So, there's different ways of looking at whether there's progress or not. Now, one of them, this is what we always thought, that science progresses kind of at the same speed over time. And each scientist is finding out a little something new, and you add all these things up, and then when you go and start studying it as a scientist, you're already actually on top of the shoulders of all these other people that came before you. You're not going back to basics and discovering what the first person, in terms of a theory, found. Okay? Now, there's others models where it's discontinuous. People for a long time think reality is a certain way, and then suddenly it completely changes. Gravity was a perfect example. There was Newtonian gravity, discovered, I think he basically wrote the paper Principia in 1665. And then it wasn't until Einstein came along in 1915 with his general theory of relativity, which is another theory of gravity, that it actually changed. And the difference between Newtonian and Einsteinian gravity is huge. Okay? I mean, it's completely different. So it's kind of like it was a discontinuous model. People, all of a sudden, with Einstein, who had this incredible imagination, came up with a whole new way of looking at things. It's called a paradigm shift. In other words, your kind of point of reference has completely changed. There's actually evidence for both, by the way. Now, the thing is, how might technology perceive or change your perception of the universe? Could anybody imagine small, tiny, invisible organisms before someone invented a microscope? What's the chance of that? No. So before that, people thought, as far as disease, that, well, we got diseases because someone put a curse on you, right? Witchcraft. And the only way to actually get rid of the curse and get better was to find some other witch who would take the curse off. It was also thought at the time that there was this balance of different humors, bile, which came from the liver, blood, but I think there are 4 of them. And so people in the old days, they would bleed people because they thought that if they got sick, their humors were out of balance, and by bleeding them, it would actually put their humors back in balance. And of course, more often than not, they would make them weaker and would oftentimes kill them. You know, you go in, you've got a terrible disease, and your immune system might actually protect you, but you've already bled yourself, you've made it an insult to your system, and you end up dying, okay? That all changed once someone realized there were these little things, and then someone else said, maybe these little tiny animalcules, they called them, actually cause disease. And this was the beginning of the germs theory of disease. And it changed everything. Once people accepted this new theory, it had certain implications. First of all, don't bleed people. Because there's germs everywhere, people should be living in more sanitary conditions, and if they go into the hospital, doctors should wear gloves and make sure that they're not spreading germs around. Okay? So, same thing with telescopes. As you know, in the beginning for the most of human history, people probably thought, if they thought at all, that we were the center of the universe and everything, the stars and the sun and the moon revolved around us. Well, that started to change with telescopes. Galileo saw the rings of Saturn and the moons of Saturn. And he realized that Saturn was a planet, and there were actually smaller objects circling around it. And they extrapolated to, well, maybe what we're actually seeing here on Earth is that our Earth is actually spinning, and that's why it looks like the universe is going on around us. So, oftentimes, technology can actually change. You can't imagine what things are. A good example is, in astrophysics, there was a certain model of how solar systems formed and the kinds of planets you're going to find in certain places. It was all based on a sample size of 1, our solar system. Rocky planets close by. Farther out you go, you get these gas giants like Jupiter, Saturn, Neptune, Uranus, things like that. We thought, okay, and then we had models to explain how you end up with a solar system like that. Well, about 10 years ago, we were suddenly able to actually measure planets going around other suns. Okay? And all of a sudden we're finding these gas giants that are actually very close to the sun, closer than Mercury, and they're circling their star every 10 days. It's completely different. Now, before we had the technology to actually measure that, we had no idea. We thought we had a pretty good model for explaining things, but our view of the universe was so restricted. So technology has actually had a huge effect on even the way we formulate questions. Okay, what's a correlation? Anybody? I'm going to point to someone. Okay, eeny, meeny, miny, mo. What's a correlation?
It's like something happens and it affects another thing happening.
Mm-hmm. Okay, so kind of cause and effect, right? This thing happens, and then normally this thing happens, and this first thing caused the second thing. Okay. Yeah.
But that's not always true. Correlation isn't always causing.
Exactly. Okay. Correlation can maybe imply cause, but oftentimes doesn't. Do you think there's a correlation between body weight and height? Anybody?
Yeah.
Yeah. Okay. Does body weight cause height, or does height cause body weight? They're actually measures of the same thing, size. They're different measures of size. They correlate. Obviously, people who are taller usually have more body mass. Now there's variation in between. There are tall people who are really skinny, and there are tall people who have really big bodies like football players, and lots of muscle or lots of fat, and it goes the same way, all up and down the scale. So it's not a perfect correlation, but if you actually plotted it out, everybody's body weight and height on a graph, I will do it. So here we are, I just talked about, on the horizontal, this right here, that's the x-axis. On the vertical, that's the y-axis. On the bottom we have height in inches, and on the y-axis we have weight in pounds. And all these little dots are different individuals who have a certain height and a certain weight together. So they're plotted along there, and you can see that there's an increasing slope. That means usually the taller you are, the more you weigh. Exactly. But there is variation all along what we would call the mean correlation line, or the correlation coefficient. Okay? Oh, that's what's going on. Okay, now I see. Never mind. Okay. So, you can do the same sort of plot, drugs and violence on the bottom, and on the side, songs about those sorts of things, or the other way around. And you would see a sort of correlation there. There seems to be a correlation. The more you experience violence, the more you listen to rap music, or the other way around. So a correlation can imply cause and effect. In fact, in this case, it's probably both, or doing both. But more so, the violence is probably having a bigger effect on causing people to listen to rap music than the other way around. Okay? So you can then, if you see a correlation, you can actually test that by setting up a real experiment. Strychnine, and I give it to someone, they'll be jumping off the walls before they die. I give them a large enough dose. It's a toxin. Plants use it a lot to defend themselves. They don't know they're doing it, but that's what they do. In this case, you could actually say that taking strychnine will make you sick. One thing will cause another. It's not that you're sick and so you go ahead and take strychnine in this case. Though sometimes people do, like with the bloodletting. I'm sick, I'm going to go have someone bleed me to make me better. In this case, being sick is the cause. So you have to make sure that there's actually a plausible explanation, and you're not just kind of moving things around. So, in the late 80s, rap music was most associated with inner city, violent crime, drugs. The same thing happened on TV. And it was thought that songs about drugs and violence, or watching a movie that's violent, will make you become more likely to do drugs and be violent. And I can attest to you that it's true. Okay? whenever I start doing rap, I suddenly become violent. I don't know why. I do the same thing though when the sound of music comes on, you know? And for some reason that makes me violent too. I don't know, it's just weird. Okay, so is it plausible that songs about drugs and violence cause violence? What about the other way around? What if you're getting these songs because people are writing songs about what they're doing? They're living in a violent society. And they're taking lots of drugs. So what's cause and effect here? Can you determine if it's really... So with a correlation, you might see that there's a correlation between songs about violence and drugs and the amount of drugs being used. People who regularly wear seatbelts are more likely to be diagnosed with cancer than those who do not wear seatbelts. Now, we were talking about correlation between different things. In this case, we would say seatbelts or wearing seatbelts increase the risk of cancer. Doesn't make much sense, does it? But seatbelts are actually correlated with something else as well. And what do you think wearing seatbelts are correlated with? Well, seatbelts are actually correlated with longer lifespan. And as you age, you increase, first of all, you have more time for cancer to actually start. And then as you get older, you have an increased risk of developing cancer as well. So it's not that seatbelts cause cancer, they just allow you to live longer, and that means that wearing them, you're probably more likely to get cancer. Now, if you want to avoid cancer, I would say just don't wear seatbelts. In fact, you might just want to step in front of a bus or something. You'll never get cancer after that. You don't even have to worry about it. Okay, so here we are. Here's the actual diagram. And you can see actually what you might say is actually correlated. If we were to put our graph together here, you wear a seatbelt, you live longer, so we'll just say this is years up here, and the number of times you wear a seatbelt. And you can actually see, there's kind of this. So, seatbelt and living longer is correlated, okay? In fact, we can actually say that probably seatbelts cause you to live longer. We'd have to do this sort of experiment to prove it or to show that that's actually the case, but it certainly makes logical explanation. So, instead of actually saying, though, that seatbelts cause cancer, which they don't, it's actually living longer that causes cancer because you have more time to develop it, as I said, and more time as you get older, a greater likelihood of developing cancer in the first place. Therefore, when we're talking about correlation, it does not necessarily imply causation. If there is a correlation, you might say, well, maybe one thing does cause the other. So in this case, A, for example, is correlated with B. Or B is correlated with A. Does A cause B? Or does B cause A? Okay? You can only do that by doing an experiment or showing that, in fact, that is most likely the case. The thing is, one thing that you might think, as I just showed, was that as something might actually be correlated with another variable that is actually the cause, as in this case. Seat belts, wearing seat belts make you live longer, and living longer increases your risk of cancer. Okay. And then, anybody know what's an anecdote? Huh? What's an anecdote?
Story.
It's a story. My grandmother, during Christmas, always gets a cold. Or my grandmother always took vitamin C and never got a cold. What's the sample size with that? 1. Is anything else controlled for her? You don't know if she actually took vitamin C or not, right? She could be lying. She actually took echinacea, and that had as much effect as vitamin C. No effect at all. It turns out she had a better immune system than my uncle Whiting. Whiting didn't have a good immune system. So when he got a cold, he finally got pneumonia and died. Had nothing to do with one took vitamin C or echinacea, and the other one didn't. It just so happened my grandma had a great immune system, never got sick. My uncle Irving got sick and got pneumonia and died. Right? So now, if you see enough anecdotal evidence, let's say with a correlation, then you can start looking at it. But an anecdote by itself doesn't prove or suggest anything that's actually concrete. To actually go and figure out whether an anecdote, there might be something to it, you have to replicate, have a huge sample size. Okay, so where is an anecdote in this flow chart? Anybody? Come on, just you can be wrong. I swear. So I'm not gonna take any. I'll give you an extra point if you just say, where is an anecdote on this flow chart? Huh? Hypothesis? Observation. So, who says hypothesis? Who says observation? Okay, in this case, unlike believing that the universe went around the center of the universe is the Earth, it's observation. It's just one data point. That's all it is. It's one, doesn't mean, if you pick hypothesis, I don't care. You just learned something, right? Doesn't mean that you're an idiot for thinking that. This is how you learn stuff. It's great. For those of you who thought it was a hypothesis, you actually learned something that everybody else didn't. Look down on those people. Okay? No, so on that anecdote is an observation. If you get enough anecdotal observations, you might think, oh, there's something there. Right? Living next to a chemical factory, suddenly cancer cases start showing up. Well, it's anecdotal, but let's say that company has chemical factories all over, and wherever they are, these clusters start showing up. Then you can actually do some experiment. You can at least do an observational study to show that, well, yeah, there seems to be a correlation there. Okay, that's the end of that. Now, let's go back to